Now to the extraordinary images tonight, the scare for visitors at Yellowstone National Park, the very close call with a geyser raining down rock and debris. Here's ABC's Mola Lengi.
Molten movement beneath the western United States has long captured the attention of scientists and the public alike. When the United States Geological Survey issued a red alert following the detection of unusual geothermal activity connecting Yellowstone to Mount Rainier and Mount Hood, the world's eyes turned toward America's volcanic heartland. Satellite instruments picked up an extensive network of magma tunnels stretching deep beneath the surface, tunnels that seemed to link the immense magma reservoir beneath Yellowstone with those feeding two of the Pacific Northwest's most iconic peaks. The revelation ignited concern among volcanologists, geologists, and emergency planners who recognized the magnitude of what this might mean for the continent's geologic stability. Before we start, smash the like and subscribe buttons for more updates. Yellowstone has always been the centerpiece of America's volcanic story. It sits atop a supervolcano capable of reshaping continents, a vast subterranean cauldron where heat and pressure have been building for hundreds of thousands of years. The caldera itself spans over 30 miles, a remnant of an eruption so powerful it ejected hundreds of cubic miles of rock and ash into the atmosphere. For decades, scientists have tracked the restless magma chambers beneath Yellowstone, noting the slow rise and fall of the ground, the tremor swarms that ripple through the region, and the release of gases hinting at changes below. Yet this time, what set alarms ringing was not just local activity. It was evidence of subterranean connections stretching north and west, weaving a hidden network between Yellowstone and distant volcanoes that were never thought to share the same source of molten material. The satellites first detected faint thermal anomalies running in linear patterns beneath the crust, anomalies that matched the heat signatures typical of magma flow. Using interferometric radar and gravity mapping, analysts realized these were not isolated hotspots. Instead, they were part of a continuous corridor, a channel of partially molten rock extending for hundreds of miles. At depths of 10 to 15 miles, the tunnels seemed to pulse with movement, their temperature readings rising by several degrees over a matter of weeks. The alignment led directly toward the Cascade Range, where Mount Rainier and Mount Hood loom over the Pacific Northwest. Mount Rainier, though tranquil on its surface, has always been known for its potential danger. Covered in thick glaciers, it poses one of the greatest lahar risks in the continental United States. Mount Hood, less massive but equally complex, has a deep magma system that occasionally stirs with seismic murmurs. Both volcanoes belong to the Cascade Volcanic Arc, born of the slow subduction of the Juan de Fuca Plate beneath the North American Plate. Traditionally, the Cascades and Yellowstone were seen as separate volcanic systems, powered by distinct geological processes, one by subduction, the other by a mantle plume rising from deep within the Earth. The discovery of a connecting magma corridor blurred that line, suggesting a level of geological interaction that defied decades of scientific consensus. When the USGS issued its red alert, it wasn't out of panic, but out of prudence. The color-coded system signifies the highest level of concern, indicating significant underground activity that could lead to eruptive changes. Red alerts are rare, especially when involving multiple volcanic centers. The agency emphasized that the data did not necessarily predict imminent eruptions, but the mere presence of such a connection implied that the energy systems beneath the continent were interacting in ways not previously understood. The implications stretched far beyond volcanology. They reached into climatology, ecology, and even national security. Scientists gathered in emergency briefings to interpret the findings. They examined satellite overlays showing the glowing streaks of magma corridors beneath the Rockies and Cascades. The models revealed zones of partial melt connecting Yellowstone's lower chamber to a secondary reservoir beneath central Idaho, then branching toward the Columbia Plateau and splitting toward Rainier in Washington and Hood in Oregon. This was not a uniform tube of molten rock, but rather a series of interconnected pockets, linked by conduits where pressure and temperature aligned just right to keep rock in a viscous, mobile state. Such structures had been hypothesized before, but never confirmed. Magma tunnels of this scale could allow heat and fluid transfer across vast regions, potentially synchronizing volcanic behavior across hundreds of miles. A pressure increase in one chamber might subtly influence another, creating cascading effects. This could explain why, in recent years, tremor swarms in Yellowstone had occasionally coincided with seismic stirrings in the Cascades. What once appeared to be coincidence now seemed like the flickers of a shared heartbeat beneath the continent. Geologists began re-examining years of seismic data. They noticed that certain harmonic tremors, a type of rhythmic vibration associated with magma movement, had been recorded simultaneously in distant regions. It was as though deep beneath the crust, the Earth was exhaling through multiple vents at once. Fluid dynamics simulations suggested that if the tunnels were indeed allowing pressure exchange, the entire volcanic corridor could behave like a massive, interconnected system. This raised questions about the stability of the region and the long-term evolution of the North American plate. The energy stored within Yellowstone's magma system alone is staggering. Estimates suggest that it contains enough thermal energy to power the entire United States for millennia, if harnessed safely. When that energy becomes dynamically linked to other volcanic systems, it represents not just a geological curiosity, but a continent-wide reservoir of potential change. The redistribution of magma and heat could alter fault patterns, surface deformation, and hydrothermal circulation. Rivers, aquifers, and even ecosystems could shift in response to subtle crustal movements driven by forces miles beneath the ground. For the USGS, the red alert meant activating the full suite of monitoring systems. Drones equipped with spectrometers were deployed to measure gas emissions over large swaths of terrain. Anomalies in sulfur dioxide and carbon dioxide levels were detected not only in Yellowstone, but near Mount Hood's fumaroles and along the western Snake River Plain. Scientists speculated that gases might be migrating through the same conduits as magma, a phenomenon rarely observed at this scale. The presence of helium-3, a rare isotope often associated with deep mantle sources, was particularly telling. It confirmed that these systems were not isolated but shared a common mantle-derived source feeding upward through multiple crustal layers. In the public sphere, fascination mingled with fear. The thought of a subterranean network linking three of the most powerful volcanoes in North America evoked images of vast geological mechanisms stirring to life. Yet scientists urged caution in interpretation. While the discovery was extraordinary, it did not mean that eruptions were imminent or that the systems were merging into one supervolcano. Rather, the tunnels indicated that energy could be transferred more easily than previously thought, allowing localized pressure relief that might actually reduce the chance of catastrophic failure. Still, the prospect of interconnected magma flow changed the way geologists viewed continental dynamics. The formation of such tunnels can be traced to the deep processes shaping the Earth's mantle. Over millions of years, the Yellowstone hotspot has migrated eastward relative to the North American plate, leaving behind a trail of volcanic scars stretching from Oregon through Idaho to Wyoming. These ancient calderas marked previous eruptions, each separated by hundreds of thousands of years. As the plate moved, residual heat and partially molten material lingered in its wake, creating potential channels where newer magma could migrate. Over time, as tectonic stresses shifted and crustal weaknesses evolved, some of these ancient pathways may have reactivated, forming the tunnels now detected by satellites. Understanding how these tunnels formed requires examining both geological and thermal conditions. Magma movement through the crust depends on gradients of pressure, temperature, and density. When hot, buoyant magma encounters cooler, brittle rock, it can create fractures and melt corridors, slowly expanding its route through the subsurface. The recent increase in geothermal flux detected in the region suggests that mantle upwelling beneath Yellowstone may have intensified, pushing more heat outward along structural weaknesses. The Columbia Plateau basalts, remnants of one of the largest lava floods in Earth's history, provide a precedent for how mantle plumes can inject enormous volumes of magma across vast distances. The new findings hint that similar processes, though slower and deeper, are still unfolding today. For volcanologists, the greatest concern lies not in eruption, but in the transfer of energy. Magma that moves horizontally through the crust can cause significant deformation without ever breaking the surface. This deformation can alter stress fields along faults, potentially triggering earthquakes or hydrothermal explosions. In regions like the Cascades, where glacial meltwater interacts with volcanic systems, sudden changes in temperature and pressure could destabilize slopes or increase hydrothermal activity. Thus, even in the absence of eruptive behavior, the effects of a connected magma network could ripple through the entire western landscape. The discovery also challenges the way scientists think about volcanic isolation. Traditionally, volcanoes were studied as independent entities, each with its own plumbing system and magma source. The realization that they may share interconnected channels means that volcanic forecasting must adopt a more holistic approach. Instead of monitoring single peaks, geologists may need to view entire provinces as integrated systems, where changes in one sector can influence the behavior of others hundreds of miles away. In the academic community, the findings spurred a wave of research proposals. Universities and geological institutes began planning field studies to collect rock and gas samples across Idaho, Washington, and Oregon. Advanced seismic arrays were proposed to map the subsurface in greater detail, using algorithms capable of detecting even the faintest harmonic vibrations. Theoretical models of mantle convection were being rewritten to accommodate a multi-branch plume feeding multiple volcanic centers simultaneously. The possibility that the Yellowstone hotspot interacts dynamically with the Cascade subduction zone redefines what scientists know about plate boundary processes. From a planetary science perspective, this discovery also offers a glimpse into how continental interiors evolve over geologic time. On other planets, such as Mars and Venus, vast volcanic systems once dominated surface reshaping. The tunnels beneath Yellowstone, Rainier, and Hood may represent an early stage of similar processes, a continental-scale reorganization of heat and material that could alter the face of North America over millions of years. It demonstrates that even in a seemingly stable region, Earth's interior remains alive with movement and transformation. The practical implications reach into energy research as well. If magma tunnels do facilitate heat transfer between deep sources, they might influence the potential for geothermal energy extraction. Some researchers argue that understanding the pathways could allow for safer and more efficient tapping of subterranean heat without disturbing sensitive regions. However, this must be balanced with the risks of inducing seismic activity or altering delicate hydrothermal equilibria. The USGS and Department of Energy began discussing frameworks for collaborative monitoring, ensuring that any exploration respects the complex dynamics now known to exist beneath the western United States. Local populations near Rainier, Hood, and Yellowstone have long lived with the awareness of their geological neighbors. For them, the red alert brought a renewed focus on preparedness. Emergency management agencies updated contingency plans for potential ground deformation, gas emissions, and increased seismicity. Communities held town meetings where scientists explained the discoveries in accessible terms, emphasizing vigilance without alarm. The message was consistent. This was an extraordinary scientific revelation, but not a harbinger of disaster. Still, the imagery of molten tunnels weaving through the continental crust captured imaginations worldwide. Artists, writers, and documentary filmmakers flocked to the region to interpret the event through creative lenses. It became a symbol of nature's unseen unity, the way forces beneath the surface connect distant landscapes and shape destinies in silence. Beneath forests, rivers, and mountains, a vast system of molten arteries pulsed with life, reminding humanity of the deep continuity that binds the planet together. The red alert also highlighted the power of modern observation technologies. Satellite interferometry, thermal imaging, and gravity mapping now allow scientists to see the Earth's interior in unprecedented detail. In past generations, such a discovery might have gone unnoticed until eruptions forced attention. Now, humanity can witness the slow dance of magma in real time, tracing the breath of the planet through its subtle thermal and seismic signals. This capability marks a turning point in geological science, one where prediction becomes less about fear and more about understanding the living Earth. In the weeks following the detection, the data continued to evolve. Temperature readings along the corridor stabilized somewhat, suggesting that magma movement had slowed or reached equilibrium. However, residual gas emissions persisted, especially near Rainier's southern flank and Hood's fumarolic vents. This ongoing activity kept scientists alert, monitoring for any signs of renewed movement. Periodic tremors in Idaho and minor quakes along the Cascade foothills hinted that the system remained active, though not escalating. The intricate structure of the tunnels fascinated geophysicists. Cross-sectional models revealed that the conduits varied in thickness from a few hundred meters to several kilometers, depending on local rock composition. Some portions appeared to follow ancient fault lines, using pre-existing weaknesses as pathways. Others seemed to carve new routes through ductile rock layers softened by heat and fluid infiltration. The geometry of these tunnels suggested that magma was not moving in a simple flow, but pulsating in cycles, advancing and retreating as pressure equalized. This pulsation pattern may hold the key to understanding why the connection formed in the first place. Pressure buildup beneath Yellowstone could have forced magma outward in search of escape routes, while cooler, denser crust near the Cascades created a natural gradient for flow. Over time, these competing forces established a thermal bridge, a self-organizing system that balanced the immense energy differences between regions. Such dynamics reveal how nature constantly seeks equilibrium, even in the most volatile of processes. One of the most intriguing aspects of the discovery lies in its implications for mantle plume behavior. The Yellowstone plume has been a geological mystery for decades. Some studies suggest it originates as deep as the core mantle boundary, rising through the mantle like a column of heat. Others argue it's a shallower feature related to regional convection currents. The newfound tunnels support the idea that the plume interacts laterally with surrounding structures, feeding multiple volcanic systems rather than rising in isolation. This could mean that what scientists have considered a single plume may actually be part of a sprawling mantle network, an intricate web of upwellings shaping the western United States from below. Environmental scientists, too, began considering how such subsurface changes might affect the surface biosphere. Alterations in geothermal gradients can shift soil chemistry, groundwater temperature, and gas composition. In Yellowstone's thermal basins, microbial ecosystems depend on delicate balances of heat and minerals. A redistribution of subsurface flow might transform these habitats, creating new microbial colonies while extinguishing others. Similarly, the Cascades' subalpine zones could experience subtle changes in water chemistry as gases migrate upward through fractures. These shifts might seem minor on human timescales, but represent profound changes in the slow evolution of landscapes. From a cultural perspective, the link between Yellowstone and the Cascades also carries symbolic weight. Indigenous communities across these regions have long held stories of underground fire, sacred mountains, and the interconnected breath of the earth. For many, the scientific discovery resonates with these ancestral understandings of nature's unity. Elders and cultural historians have pointed out that traditional teachings often spoke of fire spirits traveling between mountains, a poetic echo of the magma corridors now revealed by satellites. The convergence of ancient wisdom and modern science deepens humanity's relationship with the living planet. The Red Alert became a call for cooperation among nations and disciplines. Volcanologists from Japan, Iceland, and Italy offered expertise from their own experiences with complex volcanic systems. Data sharing agreements were expanded to ensure global collaboration on magma monitoring. The discovery reminded the scientific world that Earth's systems transcend borders. Understanding them requires collective effort. In this sense, the tunnels beneath the American West became not just a geological phenomenon, but a symbol of global scientific unity. For the general public, the revelation rekindled a fascination with Earth science. Enrollment in geology programs rose as students sought to understand the forces shaping their planet. Museums created immersive exhibits showing three-dimensional visualizations of the magma tunnels, allowing visitors to walk through virtual versions of the underground corridors. This renewed interest in geoscience brought attention to the importance of funding for research, monitoring, and education, tools essential for navigating a world where natural processes continually remind humanity of its place within a vast, dynamic system. The magnitude of the discovery also raised questions about human resilience. What does it mean to live atop a planet that is constantly reshaping itself? The realization that distant volcanoes might share a single pulse serves as a humbling reminder that stability is often an illusion. Yet it also reveals the remarkable adaptability of life and civilization. People continue to thrive in regions shaped by fire and ash, turning potential danger into a source of learning and wonder. The USGS's response underscored the value of scientific transparency. By releasing data promptly and communicating clearly, they prevented misinformation from overwhelming the discourse. Their reports detailed the precise nature of the findings: magma pathways detected at depth, energy redistribution without evidence of surface eruption, and ongoing monitoring to refine understanding. This openness built public trust and fostered dialogue between scientists and citizens. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on magma tunnels connecting Yellowstone to Rainier? We want to hear from you. Thank you for watching and see you next time.